Hi everybody, welcome to day 3 of your notes video lessons. We are going to be talking about transformations of functions, and this is going to follow really closely after what we just did today in class. Today we graphed parent functions, so functions like just a linear function. We could have quadratic function, we could have cubic, so on and so forth. And so remember, first off, that we pronounce this f of x, meaning we have a function as it relates to the variable x, because that's the variable I'm writing in the function. Kind of same thing, though, as what we've maybe traditionally thought of as the y. Okay, it's just a little more specific. So all functions, okay, come from a parent function, right? Kind of like we can think of the original. Think of it like parents and kids, right? Kids all come from somewhere. So we start with the parent, and then those parents have their kids, right? And they look different and act a little different, but they still came from that original parent, okay? So it's the same thing with these functions. We have our parent function, and then we can use these transformations to make them look a little bit different, okay? But they still came from the original parent function. Okay, so what kind of transformations can we do? Well, we have vertical shifts, horizontal, reflections, stretching and compressing. We actually transformed lots of different functions last year in Algebra 2. We did kind of the same thing over and over again, you might remember. So quite a bit of this actually is review. Okay, so let's talk about the transformations. So if we have transformations happening in the vertical direction, we're going to call those vertical shifts, or in other words, in the y direction, okay? So if we're affecting the y, it is a vertical shift. And then if it's affecting the x, then we're going to have a horizontal shift, okay? So we have vertical shifts when we are making changes outside that are not attached to this x that we see here. So notice, okay, we're adding c and subtracting c on the ends. We're not doing that on the inside of the parentheses attached to x. So that's how we know these are vertical changes. If we're adding a number, then we're moving up c units. Okay, if we are subtracting some number c, then we're moving down c units. Okay, so c is just some number. Well, what does that look like on the graph? Okay, so on the left-hand side, if we're going to be moving up, notice I'm not going to change how wide or skinny the graph is. I'm just going to take this point here and move it up. Okay, so basically every point on our graph would move up. Sorry, I'm not the greatest drawer. Okay, but again, so notice it's same shape with all that good stuff. We just moved every point up 2. I don't know why I said 2. I just made that up. We've moved every point up c units, but it could be 2. Okay, what about down? Well, same thing. We're just going to take every point, move it down however many units. Okay, so notice, again, graph, same shape and everything. It's just shifted down. All right, well, what about horizontal? So if we are subtracting or adding a number on the inside, okay, so attached directly to our x, well, x, right, think of the domain. That's left and right movement, okay, that's horizontal. So we're affecting those x values. Now, we are going to think opposite. So if we're subtracting a number, then think opposite of what vertical was. We're actually moving in the positive direction. So positive horizontally would be to the right. And then if we're adding a number in the inside, that means we're moving negatively. So we're going to be moving to the left. Okay. If you have a graphing calculator at home, you could absolutely type in, random numbers for C, add, subtract, and see how that shifts your parent functions around. Okay, so if we're moving to the right, again, we're not changing the shape or anything. We're just taking all these points and moving them however many units to the right. Okay, so notice all these points just moved a little bit over. Okay. And now if we're moving to the left, then it might look something like this. Okay, and that's if we add a number on the inside. All right, so I don't know if you can hear my cats in the background, but my boy cat is having the zoomies right now. He is running everywhere crazy. So if you hear craziness in the background, that's him. All right, anyways, moving on. So now we have reflections. So if you hear the word reflection, automatically think that we're multiplying by a negative, okay? Or if you see a negative, automatically think the word reflection. Okay, so if the negative is on the outside as such, again, think vertical. So if we're reflecting vertically, that means I'm taking my graph and I'm flipping it either up or down. Okay, so let's draw that. So if I take this graph here on the left and I flip it down, okay, well, what axis did this just hop over? Well, that hopped over the x-axis, okay? So for vertical reflections, those are going across the x-axis. Okay, so don't let the fact that there's an X there make you think it's a horizontal reflection. No. Picture it in your head. If I'm reflecting vertically, okay, imagine a graph flipping over up and down. What axis is that? That's the X. So now if it's on the inside, like this, that means we're reflecting horizontally. Anything on the inside is horizontal change. So if I'm reflecting horizontally, that means I'm flipping over left or right. And so that could look something like this, okay? And notice that that flipped over the Y. All right. Another type of change we have is a vertical stretch or compression. So again, vertical, that's on the outside. And so we see here that there is some number C being multiplied on the outside. Okay, so if it's being multiplied, you know it's a stretch or compression. If it's on the outside, it's vertical. Okay, now if that number is greater than 1, like 2, 3, 4, 4.5, then that is going to be for vertical a stretch. Okay, so think about just, on a simple, graph, okay? Think of these stretches and compressions almost like slope, right? Kind of the rate at which we're changing. So if we have an original, just regular line, okay, if we stretch this vertically, okay, then we're going to be getting a larger slope. It's going to be increasing at a faster rate. Okay, so you might get something a little more steep like that. Okay, so for vertical stretches, another thing, think of like a rubber band. Okay, if you have a rubber band and you're holding it up and down, okay, one hand on top, one hand on bottom, and you stretch it, the graph gets skinnier. So what does that look like? Well, let's look on the left-hand side here. If I try to stretch these curves, I don't want to move it left or right at all or up or down at all. So I do want to try to go through these key points here. I am just simply making it stretch. Okay, so think of rubber band stretching. Notice it's skinnier, but I'm still through those same key points. Okay, and notice that my maxes and mins are occurring at the same x values. Okay, so they're both occurring at these x values. Okay, well, what about a compression? So if we have a number that is less than 1, okay, a fraction less than 1, but greater than 0, that's a compression. Think of a rubber band. You have that hand on top, you have that hand on bottom, and now instead of stretching it, you're compressing it, like smushing it down. Okay, the graph is, or the the rubber band is going to get, it's going to look a little smushed down, right? It's not going to be as narrow and tall. So what does that look like? Well, on the right here, again, okay, that would be if we have a fraction. So I'm going to still, again, go through these same points. We're not doing any translations, meaning we're not moving left or right. That was horrible. Let me try again. Not much better, but oh well. So notice it's just less tall. It's not as narrow, okay? But I'm still going through the same maxes and mins, just as the other. Okay, so that's vertical stretches and compressions. Well, what about horizontal? Okay, so horizontal, that's going to be if we have a number being multiplied on the inside attached to x directly. And for horizontal, just like kind of for translations, the left and right movements and up and down, think opposite, right? So if we have a number c and it's larger than 1, well, for vertical, that was a stretch, but for horizontal, that will be a compression. Okay, and then if we have a fraction between 0 and 1, like 1/2, 1/4, that's going to stretch the graph. Okay, and so we can think of a rubber band on its side. So our hands are now on the left and right of the rubber band. And imagine taking your hands and stretching it. Well, that means that rubber band, yes, it's getting stretched left and right, but when we stretch that rubber band, that rubber band is now not going to be as tall, right? Whereas then if we take that rubber band and we smush it together with our hands on the left and right, and I recommend grab a rubber band, do this yourself. If we take our hands on the left and right, smush them together, that graph is going to get taller and narrower in the vertical direction, but compress in the horizontal direction. Okay, so kind of just maybe I'll draw a little, imagine this is the rubber band. We're holding it right here. Let me draw a little hand. Oh my gosh, that looks like a flower. This might be a horrible idea. Okay, if I take these and I compress, okay, then my rubber band, okay, now is kind of looking more narrow, skinnier, vertically, but closer together horizontally. Oh my gosh, I can't even look at these horrible drawings. I've got to take them off. Oh gosh, okay. Anyway, so let's see what these look like on, oh, one other thing. Notice the factors have flipped. So whereas before, our factors for vertical, the number stayed at it as is, right? So if it was a 2 we were multiplying on the outside, our factor would be 2. But for horizontal, it flips, okay? It's the reciprocal. So we're actually going to have, for this, say it was 2 was c in our being multiplied, well then our factor would be 1/2. All right, so for the compression, what does that look like on the graph? Again, think of the rubber band, think of the, just like my horrible drawing, it getting closer together with your hands on the left and right. So that might look something, try and do this the best I can. Not the best, but that'll do. So notice my origin's still the same. I'm not moving it around left or right or up or down, but notice these, sorry, I gotta draw that. It's horrible. Okay, but notice, okay, that my blue line is shorter, more compressed than my original. Now the important thing here is, whereas before I drew those lines up and down, right? We drew them up and down, the maxes and min occurred at the same x values. Now we want to make sure for horizontal, the maxes and mins are occurring at the same y values. Okay, so that's for the compression for horizontal. Now for the stretch, imagine your hands being on the left and right of the rubber band, stretching it out. So your graph's kind of getting longer, right? So I still want to go through the origin, but now I'm just going to draw my graph a little bit longer, and I do want to make sure my maxes and min occur at the same height as the original. Okay. All right, let's go ahead and now talk about, so these are kind of the overview of all of our transformations. We can also look at just the function itself, the equation, and see what the transformations are from there. So let's do some of these examples. Now, one thing is very important. Okay, you guys do need to write transformations in the order you approach them as you read left to right, right? We read left to right. Now, this might not make sense why that's so important in this section, but in the next, on the next page, I'll show you why it's so important we do transformations in the order that we see them. Okay, so we see here that the only thing happening is that we have a plus 10 on the end. That tells us that that is a vertical change. Since it's on the outside, we're adding, so that means we go up 10 units. All right, B, we see we're adding 10, but now it's on the inside attached to our X value. So that means, again, think opposite. If we're adding 10 and it's horizontal, we're going to the left in the negative direction. All right, C, we see the only thing here is a negative, so automatically think reflection. And now we know it's on the outside. Outside, away from the X means vertical, affecting the Y values. So if we're reflecting vertically, imagine flipping over up and down. What axis is that flipping over? If it's up and down, that's over the X axis. All right, D, same thing, but now the negative's on the inside, so that means we're reflecting in the horizontal direction. So if we're flipping over left and right, that means we are reflecting over or across the Y-axis. All right, part E. Okay, we see here we have that negative on the outside being multiplied, so automatically think reflect, and we know that on the outside that's going to be over the X, and I'm going to abbreviate this now ROX for reflection over X. Then we have this 1/3. Okay, it's on the outside, so that tells me first off that that's vertical. It's a fraction. So for vertical, if it's a fraction between 0 and 1, that's a compression. Okay, so again, imagine that rubber band. You have a hand on top, a hand on bottom. If you're compressing it, that means your hands are getting closer together. You're smushing down that rubber band vertically. And now for vertical, you keep the factor as is. So by 1/3. Okay, part F. We see that negative on the outside, so once again, reflection over X. But now that 1/3 has changed to a 3, so we know that's going to be a vertical. I'm going to abbreviate this, stretch by 3. I recommend, guys, you pause, you try the rest of these on your own and see if you get what I get. All right, G, we see that negative again on the outside. We have a reflection over X then. We also see a -2 on the outside. So that's a vertical translation. Minus would be down 2. Nothing's happening on the inside here with the X, so no horizontal changes are happening. All right, H, we see we have -2 on the inside, so that's either left or right. If it's minus, that's going to be, think opposite, right 2. And then plus 1/5 at the end would be up 1/5. Part I, we have 3 on the outside, so just like our example in part F, that's going to be vertical because it's outside, stretch because it's a number greater than 1, and factor stays the same, so by 3. -6 on the inside, right 6. And lastly, +7 on the outside, up 7. All right, next, part J. We have a 5 on the inside. So that means it's going to be a horizontal change. Now, if it's being multiplied, that's a horizontal stretch or a compression. For horizontal, if it's a number greater than 1, what is it? It's going to be a compression. And the factor, don't forget, for horizontal, you have to flip it. So it's not by 5, it's by 1/5. All right, okay. We have a 1/10 on the inside, so that's horizontal. But since that's a fraction between 0 and 1, we have a stretch. And flip your factors, so it would be by 10/1, which is just 10. All right, L, we have a negative on the outside, so think reflection over X, and a 4 on the inside, so we know it's horizontal because it's on the inside. It must be a compression since it's greater than 1, and flip your factor. So it's a weird 1/4. Notice, guys, that every time I write compression for horizontal, or for either one, whether it's horizontal or vertical, notice that my factors are always fractions, okay? So if you're writing the description, and in your description, as we're doing, you have the word compression, you should have a factor that is a fraction, okay? And then notice every time we're writing stretch, these factors are whole, or are numbers. They don't have to be whole, but they're numbers greater than 1. All right, last one. We have a 4 on the inside. So that is going to be a horizontal. Greater than 1 means compression by, flip it over. So it now becomes 4/, so it now becomes 1/4, just like in part L. We also see a -2 on the end. So that's going to be down 2. All right. So moving on. Now we're going to look at graphs and find the formula for the transformed graph. Okay, so you're given the parent function graphs, and we have to write the actual equation for the transformed graph. Okay, so part 1, we see our parent functions, that cubic function. Okay, so how do we know which one of these lines it is? Well, first off, all of these graphs are going to go through the origin. How do we know that? Well, let's say we plug in 0 for x. Well, 0 cubed is just 0. So that means when I plugged in 0 for x, I got 0 for y. So my parent function should go through this point here. Okay, and so as you can see, it's this blue line. Okay, you could also plug in something like 1. If we plug in 1 into x, well, 1 cubed is just 1. So we have the 0.11 right there. Okay, so that means this red line is our transformed function. Okay, so my goal is look at the origin. Okay, look at how the origin moves. Notice that the origin, this blue dot here, it's now down 1, okay? So I know that I need to include that transformation. It did not move left or right at all, so I'm not going to have any horizontal translations. I'm just going down, okay? Next thing we want to look at, well, what about a stretch or compression? How do I know that I have that? Well, look at the original. Think about slope, okay? The rate of change at for these graphs. So for my original, I went up 1 over 1, okay? And look at my red line here. Where I started to get to my next point, I also went up 1 over 1, okay? And then we can see that really, even just by looking, these graphs one doesn't look more stretched or compressed than the other. They have relatively the same shape, okay? So the only thing we have here is down 1. So I'm going to do that in red. It says write it as a function of g. Okay, so you do want to write g of x. All right. So there's 2 ways to write this. One is just as a general function, meaning my original function was a cubic, right? But I can just represent that by saying we have some function. It's stated here that it is cubic, so I can either write it just as f of x, or I could write it x cubed. So if you want to write it more like a general function, then you would say we have a function g of x such that whatever our original function was, f of x, it's moved down 1. Okay, and so if we want to be specific to our function that we have here, which is cubic, we will say we have a cubic function and it went down 1. Notice I'm doing -1 at the end, and it's not attached to the x in parentheses. So if you don't see any parentheses, then you know you only have vertical changes. All right, let's look at number 2. So we know the original goes to the origin, the parent function, okay? Also, let's say we plug in 1 into x. Actually, let's do, -1. Okay, well, the whole point of an absolute value is that it makes whatever our value is positive. Okay, so the absolute value of -1 is just +1. You just make it positive. So if I plug in -1 for x, I got +1 for y. So the point -1, 1 should be on my parent function graph, and indeed it is. Okay, all right. So how did my transformed graph move? So that's this line here in red. Well, again, look at the origin, guys. We see that the origin moved over to the right 2, and then it went up 1. Okay, so right 2 and up 1. I'll go ahead and start writing that function, g of x. Okay, if I'm just writing it as a general function, well, right 2 means I need to put -2 on the inside attached to my x. And up 1, that means I add 1 on the end. Okay, well, what about slope? Okay, or stretches and compression. So we can think about slope. Well, again, do this kind of same thing we did on the last graph. So if we have here that for our original, right, we see we're going up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1 every time. Well, on the red graph, starting at the origin, we're also going up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Okay, so the slope's not changing at all, meaning no stretch or compression's happening. So we can write our more specific g of x function. So we have a g of x, a function such that we moved, what was it? Oh, right 2. So I'm going to draw my bars. So right 2, make sure it's inside attached to x if it's horizontal, and then up 1 on the end. Okay. Number 3, we have an absolute value again. Okay, so we know that this is our parent function. Okay, this is going to be our transformed function in red. Okay, so notice that the origin did not move at all. Okay, so that indicates that we don't have any left or right or up or down movement. But we do notice that the red lines do look different, right, than the blue. We're a little more wide in our transformed graph. So there are actually two correct answers for this. So I'm gonna go ahead and write this. Because of the symmetry, this can be described as a vertical or horizontal change. Okay, and so when I say because of the symmetry, right, if I were to draw a line right down the middle of the graph that is symmetrical about either side. Okay, so there's a couple ways you can figure this out. So first, notice that for my parent function, right, just like the last example, we go up 1 over 1, up 1 over 1, up 1 over 1. Okay, now for my my transform function, my lines in red, I'm now going up a half over 1, up a half over 1, up a half over 1, up a half over 1. Okay, so up 1/2 over 1. So that's if I'm thinking about this vertically. Okay, so where my original, I went up 1 over 1, now I'm going up a half. So the amount that I moved up, right, is in the vertical direction. The amount that I moved vertically got cut in half. Okay, so what does that tell me? That tells me that I have a vertical compression. Okay, we know it's a compression because we have a half for 1. Okay, it's a fraction between 0 and 1. And also look at the graph. Okay, imagine that rubber band. If we are compressing the graph, it's getting wider. So we have a vertical compression by a half here. Okay, so that is one way to describe it. So let me go ahead and write that. So for a vertical compression, okay, that would look like, again, since we went up a half, and, oh, oopsie, I did not mean to do that. Since we went up a half, our factor is that we're compressing by a half. So I'm going to put that on the outside, and then nothing else is changing because we didn't have any translations, no up or down or left or right movement. So that's one way to describe it. Okay, well, what about, I said it can also be a horizontal change. So now think about what's happening in the horizontal direction. Okay, so again, where we once were, I'm going to erase this stuff. Okay, so where we once were going up 1 over 1, now think about it. Okay, so now starting from this origin here, now I'm going to think about it over 1, up 1. So now instead of going over 1, up 1, I'm going over 2, up 1. Do you see that there? Over 2, up 1. Okay, watch my pen move. Over 2, up 1. Okay, so notice when I think about it horizontally and I put the x first, I'm going over 2 instead of going over 1. But the amount that I'm moving up has stayed the same. Okay, so if I'm going over 2, that instead of over 1, that amount has doubled. Okay, but remember, with horizontal factors, we have to flip the factor, okay, do the reciprocal. So if I'm going over 2 and the amount that my x is changing is by 2 or times 2, right? It's it's doubling. Then I'm going to flip that factor. Instead of writing 2, I'm going to write 1/2. Okay. So for this would be a horizontal stretch. Okay, since not only do you notice that I'm stretched this red line, think of your rubber band being on its side and your hands being on the left and right. If you stretch it, it's going to get wider, and that's what happened here. So that's one way to know it's a stretch. Also the fact that since we were multiplying the amount we go over by 2, and that makes our factor 1/2, well, 1/2, if it's a fraction between 0 and 1, is a stretch for horizontal. Okay, so this is the same thing as writing the 1/2 x on the inside. Okay, so both of these answers are acceptable. I prefer to think about it vertically, that's easier for me, but either way is fine, okay? So if horizontal kind of confused you just then, you are more than welcome to just think about it vertically. All right, number 4. So we have a square root function, also called a radical. We know that our original is going to go through the origin here. Also, if I were to plug in 0 for x, well, what is the square root of 0? It's 0. So the point 0, 0 should be on the graph. All right, which means this is my transformed in red here. Now, let's focus on how the origin changed. Well, the origin looks like it moved over to the right one. Okay, so I know that first I know that I need to have that, okay? I also know that it flipped, okay? It flipped over what looks like to be, or what is, the x-axis. So that tells me I need a negative. All right, so if I'm just writing a general function, okay, reflection over the x means that's a vertical change, so the negative's on the outside. And then I know that I went right 1, so I need to subtract 1 on the inside of the parentheses attached to x. So if I want to be specific to the function I actually have, which here is the square root function, that negative, keep it on the outside of the square root sign. And then everything that's underneath the square root sign is a horizontal change. So I would write x minus 1. It's not necessary to have those parentheses if you didn't put those. That's okay for this example. They didn't need to be there. So meaning you could have just written it like this. Okay. And that would be our answer. All right, number 5. So we know we have a square root function, a quadratic function. We know that this is our original. Plug in 0, 0 squared is 0. Plug in 1, 1 squared is 1. Plug in 2, 2 squared is 4, etc., etc. So we see that here for our transformed line, it's definitely reflected. It flipped down, meaning a vertical reflection. So we definitely have a negative on the outside. Okay. Actually, before I do that, so I know I have a negative on the outside. We also see that the origin has moved to the right 3 and up 2. Okay, so I'm going to go ahead and write to the right 3. I'd have to subtract 3 and then up 2. Okay, well, what about stretches or compressions? Well, think about that slope. Okay, so we had here from the origin up 1/1. Well, from the origin on our red graph, we have, it's now going down since it reflected, but it's still going down 1/1. Okay, we also have up 4/2 for the original. Well, our transformed, we also go down 4/2. So the rate at which it's increasing is staying the same. Okay, so no stretches or compressions. Let's go ahead and write our function g of x specific to a quadratic. So negative on the outside, minus 3 on the inside attached to x. Don't forget to square it. We do take off for stuff like that. And add the 2 at the end. All right, number 6. We want to find a function that's finally graphed after these transformations. And guys, I told you earlier, right, I want to say right here, yep. I said to write the transformations in order as you approach them. Okay, why is that important? That's this example. We'll see why. So we have first, we're going to shift left 1 unit. Okay, so we want to, first off, we're working with a quadratic. Y is how we're, I'm going to write actually in different color. Y is how we are describing our function. So if we are shifting left 1 unit, that means that we need to add 1 inside our parentheses attached to x. And don't forget your square. Next, we see vertically compressed by a factor of 1/4. Vertically tells us that we need to have this factor on the outside. Compressed, okay, if you see compress or stretch, that tells you to multiply by whatever factor you see here. Okay, for vertical, keep the factor the same. So this tells us we are multiplying by 1/4 on the outside. Okay, so picking out those keywords will help you write the function. Next, we see down 3. So I'm going to subtract 3 at the end. And then finally, we're going to reflect it. Okay, so what we just did was steps 1 through 3. Now, many students are inclined to do this. Okay, I'm going to tell you right now, this is wrong. I bet many of us would have written it like this, okay? Well, it's reflected about the x, that's vertical, right? That means we want to multiply by a negative, right? That word reflect, think negative. We're multiplying by a negative on the outside. Well, that's what we did. So what's wrong with this, okay? Well, think about it like this. So first off, no, wrong. We A, it says that we're going to take that original, and if we're subtracting 4, that means we're going right 4. Well, which graph went right 4? This guy moved over 1, 2, 3, 4. This, look at this point here. It moved over from 3 to 7, so right 4. So it looks like this is a good match for A. All right, let's do B. We see we're adding 3 on the end, so up 3. So look at our original function. If I go up 3, 1, 2, 3, it looks like this is a good match here. It's the only one that moved it up and only up. Look at C. We see that we are multiplying by a 2 on the outside. So multiply on the outside, that tells us it's a vertical stretch or compression. It's a number greater than 1, so it's a stretch. Factor stays the same, so by 2. Plus 6, think opposite, left 6. Well, the only graph that really moved left is this guy over here. Notice that this point went over 1, 2, 3, 4, 5, 6. But it did stretch, so right, it ended up here. Okay. Also notice that this graph looks to be a bit skinnier than our original. Okay. So this looks like to be the best match for C. And then lastly, D, we have a negative on the outside, so that's a reflection over X. 2 on the inside would be horizontal. It's a number greater than 1, so that is a compression for horizontal. And the factor flips, so by a half. Okay, so remember back to that example where I told you guys, because of the symmetry, the horizontal and vertical changes were the same, right? They looked identical. That is the same for here. So this vertical stretch and horizontal compression will look similar. Okay, they're both going to make the graph look like it's more narrow. And so we see that first off, the only graph that has been reflected is this graph here. And notice it does look skinnier, as it should. So this is a good match for D. All right, guys, that is it for these notes. You do not have any practice problems after this video, but please do make sure that you maybe brush up on this stuff before coming to class next block. And I believe also, one second. Yes, because we do have a quiz next block. Okay, so just make sure to brush up on your parent functions and being able to graph those. Okay, but no homework after this video. All right, guys, have a great